Okay, today we are going to discuss about the evaporation separation using hydrophilic polyvinyl alcohol nanocomposite membrane. The hydrophilic, we are going to the details of presentation. This is our institute, Amal Jyoti College of Engineering, and this is our Amal Jyoti Center for Nanoscience and Technology. Here we are doing a lot of research based on polymers, polymer nanocomposites, nanomaterials, and nanomaterials for especially for water purification, like evaporation or membrane-based separation processes. And brief outline of my presentation, that is introduction, objectives, materials, results and discussion, and conclusion, and finally acknowledgement. The separation process we can classify it into mainly two types, that is conventional separation process and membrane-based separation process. Compared to the conventional separation process, the membrane-based separation process is efficient, practical, economic, and it is eco-friendly. There are a number of membrane-based separation process, that is reverse osmosis, membrane filtration, nanofiltration, particle filtration, and evaporation. What do you mean by evaporation? Evaporation is a membrane-based separation process in which we can able to separate azeotropes, cross-boiling liquids, stereoisomers can be selectively separated based on their permeation and followed by evaporation. That is, selective permeation occur, and it is mainly depends upon the properties of the membranes, and there is selective interaction begins, that is sorption, diffusion, and evaporation, and that combinedly known as evaporation, selective permeation followed by evaporation. So why the evaporation separation of organic and water is so important? What is the need of this evaporation separation of? Here we are mainly focusing on separation of water from organic, because as we know, because a lot of organic materials or organic solvents are used in solvents, in fermentation, adhesive printing, in pharma coatings, and chemical intermediate laboratory, and it is easily miscible with water, and it is discharged to the environment, but it causes environmental pollution or toxic to the aquatic plant. Why we are using this evaporation, we can able to separate this water from this organic, even from azeotropic mixture we can able to separate organic, and we can regenerate or purify this one water, or we can regenerate this solvent. That is the advantage of this evaporation process. In evaporation, the selectivity of a membrane is very important one, and it is good chemical resistivity is there. Usually we are using polymeric material to manufacture a good evaporation membrane, and the properties of the polymer is improved by adding nano fillers or conventional fillers. Mainly we are focusing on adding nano fillers. In our focus on mainly on the hydrophilic nanofillers into the polymer vinyl alcohol nanocomposite membrane. What is the importance of this hydrophilic membrane? We prepare a hydrophilic polymeric nanocomposite, and this hydrophilic polymeric nanocomposite form a selective interaction with the water. That is the importance of this hydrophilic polyvinyl alcohol nanocomposite membrane. And we are using bentonite nanoclay, POS, and graphene oxide, and functionalized multi-walled carbon nanotube as the reinforcing phase, and improve the properties of base polyvinyl alcohol nanocomposite material. The natural graphene oxide is prepared from natural graphite by Hammer's method, modified Hammer's method, Tooth's method. We are using. Then POS, another very interesting material is POS. We are using this POS hydrophilic in nature, and this POS is a tiny pore-like structure is there. You can able to separate water selectively from a water organic azeotropic mixture. And in our lab, we are mainly depend on solution casting method for the synthesis of polyvinyl alcohol nanocomposite membrane. Here we have 5-8% polyvinyl alcohol. Then it is cross-linked with glutaraldehyde. Then we are adding different nano fillers like bentonite nanoclay, graphene oxide, and POS, and prepare PVA nanocomposite membrane. So schematic for the preparation of this polyvinyl alcohol, graphene oxide or polyvinyl alcohol nano clay nanocomposite material by simple solution casting method. Varying composition we are using based on the filler, varying the concentration of the filler, nanoclay, graphene oxide, and pores, and we manufacture polyvinyl alcohol nanocomposite membrane. So first study that is published in ACS Industrial and Engineering Research, and that is about the bentonite nanoclay for the pro-operation, exclusively for the pro-operation separation of nanocomposite membrane. And from the FTIR studies, this polyvinyl bentonite nanoclay is a layered structure. And why? If a polymeric nanocomposite is formed, the intercalation or dispersion of the nanoclay in the polymeric material is somewhat significant, because if it is either intercalated or it is exfoliated. But in our present study, we get a characteristic peak of these bentonite nanoclays disappear. That is, bentonite nanoclay shows a peak around 6.09 degree with the D spacing 14.48. That peak is disappear. So it form a or peak intensity decreases. So it form a intercalated structure, but in higher concentration, higher filler loading around 35-8%, it form exfoliated structure. And nice TEM images, we can see the dispersion, fine dispersion of the nanoclay material in the polymeric matrix. And the atomic force microscopic images shows the nano and fine dispersion in the 1 weight percentage in nanoclay. Roughness value is 9.48 and 5.8% roughness value is 3.76%. And the mechanical properties increases with the incorporation of the nanoclay, bentonite nanoclay to the polymeric matrix. So it is membrane is the mechanical property in the significance of it is for the membrane stability. We can analyze the membrane stability. Another important parameter is contact angle analysis. The water contact angle decreases with the filler loading. We are adding the hydrophilic nanofiller, the contact angle decreases. So its hydrophilic nature of the cross-linked PVA nanoclay membrane is increases. So it is a better to separate water from a selectively water is permeated through the membrane, and mainly focused on the pro-operation separation of water isopropanol, water 1,4-dioxane, and water ethanol azeotropy. We are mainly focused on the azeotropic composition of water isopropanol and water ethanol and water 1,4-dioxane mixture. This is a principle of the pro-operation. So pro-operation is a three-step process. First is membrane is selective component is selectively sorbed on the surface, and it is diffused through the membrane. So the nature of the membrane is important in this selective component. Here membrane is hydrophilic in nature, so water is selectively sorbed on the surface and then it is evaporated. This is a schematic diagram for our pro-operation apparatus. Here we are collecting our permeate. So we take the membrane, then we are applying a pressure, then selective permeation occur. Then we collect the membrane permeate. By analyzing the properties of the permeate, we can able to calculate the flux separation factor and component flux. That all these parameters indicate the membrane performance and separation efficiency of the membrane. Then permeability and selectivity. This is a result of the separation of IPA water azeotropic mixture and the flux and concentration of clay. With respect to the concentration of clay, they initially at minimum filler loading, the simultaneous increment in the selectivity and flux takes place. That is the importance of this hydrophilic bentonite nanoclay. There is simultaneous increment in the flux and selectivity because it is selectively diffused through the intercalated polymeric membrane, polymeric nanocomposite. So separation efficiency increases. Also, the selectivity of the membrane is higher for 1 weight percentage filler loading. So membrane is selectively permeate water from water isopropyl alcohol azeotropic mixture, and also it selectively permeate. Also, it is able to break the water ethanol azeotropic mixture. This is bentonite nanoclay. In the study, we are using the cross-linked nanocomposite membrane, and this cross-linked nanocomposite membrane, the membrane stability increases by incorporating the cross-linking by glutaraldehyde. The membrane stability increases, but the performance of this membrane operations up. This is the Fourier transform infrared image of the cross-linked PVA nanocomposite membrane, and membrane form a nice cross-linking between the polyvinyl alcohol, nanocomposite and glutaraldehyde, and the membrane. The same image shows the fine dispersion of the nano clay in the polymer cross-linked polyvinyl alcohol matrix, and this cross-linked nanocomposite is effectively its crystallite formation, polymer crystallite formation, and the dispersion of clay fillers takes place from the schematic diagram. The nanocomposite, the thickness of the nano clay increases with increasing the filler loading. Also, this cross-linked PVA nanocomposite membrane is somewhat mechanical stable. It shows mechanical stability is there, and it is effectively its hydro contact angle also increases upon filler loading, and the contact angle of the cross-linked PVA membrane is 52, and it shows highly hydrophilic in nature. Upon cross-linking also, it is hydrophilic in nature by the incorporation of the nano clay to the polyvinyl alcohol nanocomposite, and it is the separation efficiency of this cross-linked membrane is increases with the filler loading. And with the PVA polyvinyl alcohol with the cross-linking agent, 5 volume percentage of glutaraldehyde and 2 weight percentage of nano clay shows a maximum separation efficiency. So the cross-linking also improve the membrane performance of the for the separation of bentonite nanocomposite membrane. And this is the comparison of the experimental result with the literature. From this incorporation of bentonite nanoclay, 2 weight percentage bentonite nanoclay is effectively used for the separation of as 12.5 weight percentage isopropyl alcohol water azeotropic mixture. And another, this polyvinyl alcohol membrane is used for the separation of water 1,4-dioxane. Another azeotropic mixture we have selected this one, water and 1,4-dioxane mixture, and this water 1,4-dioxane mixture, its separation factor and selectivity is increases. This 2 weight percentage in nano clay, nano cross-linked membrane shows simultaneous increase in the separation factor and the flux and its separation efficiency, because the sorption by filler is increases here. Sorption by filler is increases. So the effect of filler is somewhat significant in the cross-linked membrane. That's why the separation efficiency is increases. And the PVA nanocomposite shows higher water permeance with simultaneous increment in selectivity. And water permeance of the clay loaded membrane increased from 2.44 to 4,775 GPU for the cross that of neat cross-linked PVA membranes. So the sorption and permeation of the water molecule selectively through the polymeric membrane is increases. So schematic diagram for the interaction of the selective interaction of cross-linked. Here in a hydrophilic membrane. So this hydrophilic membrane selectively interact with the water molecule. So water is selectively sorbed on the surface. It is diffused through the surface, and we get permeate contain a lot of water. So that one same selectivity and flux is increases upon filler loading. Here in our present work, we are compared with the predictive theoretical modeling also. Here, majority and the one paper published in Journal of Membrane Science, and we are done our compare our studies with the theoretical prediction. And this one, the theoretical prediction shows the membrane in the hydrophilic nature and the permeation conductance or permeation ability of the membrane is somewhat close with the theoretical calculation for the separation of water and 1,4-dioxane. From this theoretical prediction, the hydrophilic nature of the membrane and selective permeation of the membrane, we can able to calculate. And these results also compare with the literature for the for 1,4-dioxane water system also. This PVA cross-linked PVA nanocomposite membrane shows somewhat higher intrinsic selectivity and separation factor and flux. The whole main advantage is that there is simultaneous increment in both separation factor and flux takes place. Then another interesting material is graphene oxide. We are used to study graphene oxide is prepared from natural graphite, And this graphene oxide is hydrophilic. We are choosing this graphene oxide because it is hydrophilic in nature. So graphene oxide reinforced cross-linked PVA nanocomposite membrane is prepared, and they characterize this graphene oxide by using FTIR. FTIR spectrum shows the typical geo peak around 3,335, 1,725, and XRD is typical diffraction peak of graphene is around 2 theta peak, 11.269 degrees Celsius, but the interlayer distances increases upon filler loading. So its peak shift change take place, and also intensity of the peak decreases. So if I a very exfoliated structure, a few layers also, or interesting, this one, the flake-like appearance of graphene oxide layer is shown clearly seen from the transmission electron microscopic analysis. Also, because graphene is exfoliated, or few layers of graphene is seen in the from the TEM images. Also, the presence of graphene oxide is indicated by the Raman analysis, and the Raman shows the typical G band and D band and ID by IG ratio is somewhat constant and decreases with the filler loading. Or G1 shows 1580 and D1 shows 1334. So it indicates the presence of graphene oxide or graphene layers in the cross-linked PVA nanocomposite. And AFM analysis also shows the fine dispersion of the graphene oxide on the surface characterization, because it is important to the surface morphology of the material for the evaporation suppression. So it is from analysis. And another interesting study is the contact angle analysis, because the graphene oxide is hydrophilic nature. We are adding this graphene oxide to the cross-linked PVA nanocomposite, but happen the contact angle decreases upon filler loading. So graphene with the 2-8%, and one way its contact angle is 50. That is, material is hydrophilic in nature and it is stable in nature. So what happened? Its interfacial energy also decreases. So it is effectively used for the separation of water from water organic azeotropic mixture. So it is effectively used for the separation of, here we are focusing on water, another system, that is water tetrahydrofuran azeotropic system, and with the minimum filler loading, that is around 0.58%, the simultaneous increment in the suppression factor and flux takes place. And also water flux from the total flux, the second image shows the total flux and water flux is somewhat close to each other. That indicates that the permeate, after the separation, the permeate is containing a major component is water. That indicates water is selectively permeate through the membrane. That's why the water flux and total flux is somewhat close to the closer than that of water total flux and THF. So in this system, that we get a highest flux separation factor of 875 was observed with the permeation flux of 0.393 kilogram meter raised to -1 and hour raised to -1. So water is graphene oxide, and this one is schematically represent the dispersion and interaction of the graphene oxide and PVA matrix. So this fine dispersion of the graphene is occur. That's why the separation efficiency of the membrane increases upon filler loading. So we can calculate the water permeance and THF permeance, because water permeance is higher upon filler loading, because minimum filler loading 0.58%. So THF flux is low, so that's why its intrinsic selectivity also increases for 0.58% filler loading. This system is compared with the famous Maxwell-Stefan's model, and this system indicate the diffusion coefficient of water and isotope. This is compared with the experimental and theoretical total flux value. This experimental and theoretical flux value shows the same trend, because 0.58% filler loading shows the somewhat higher separation efficiency for both theoretical and experimental value, but experimental value is somewhat lower than that of the theoretical one. So we applied Maxwell-Stefan's model for Fourier-Urton and to obtain similar trend. And thus the variation of experimental and theoretical prediction is due to the higher diffusion coefficient observing the measurement in liquid state sealing. That's why the difference, but the trend is same. So it is much with the Maxwell-Stefan's model, our present system. Graphene oxide reinforced the polyvinyl alcohol nanocomposite membranes. Also, they compare with the experimental result with the literature. This graphene oxide cross-linked PVA membrane shows higher separation factor for the separation of, because in our study we are mainly focusing on this azeotropic composition. So the separation factor is very somewhat higher than that of compared to the literature. Another interesting material is POS, polyoxide nanocomposite, and the structure of POS. We have already discussed the structure of POS. Here we are the same image of the polyvinyl alcohol POS membrane. Here the POS domains are nice. POS domains are seen from the FSM image, and so POS is well distributed through the polyvinyl alcohol. Two types of POS we are using, and this one, that's why POCP, that naming is there based on the structure and functional groups. And the permeability flux is of the POS membrane because on octameric POS is higher than that of another. But this nature of the POS and the weight percentage of the POS, upon 3 weight percentage, the permeability flux, the formation flux is increases, and it is published in Journal of Applied Polymer Science. That is another important material. And come to the conclusion, it's a nice dispersion of bentonite nanoclay, graphene oxide, POS, polyvinyl alcohol matrix by simple solution casting method, and it is showed much better evaporation performance, higher membrane permeance and selectivity obtained by minimum filler loading, more than 80%. But in the case of graphene oxide, we can able to separate 95% of water from a water organic azeotropic mixtures. So the nature of the nanofiller feed mixture filler composition plays a significant role in the operation suppression. These are the reference. These are some our research publication based on the operation. We are jointly edited one book that is recently published by elsewhere, that is polymeric nanocomposite membrane for operation. This is exclusively for operation. We are here discussed a lot of nanocomposite membranes like MWCNT, POS-based nanocomposite, then nanocellulose-based nanochitin-based nano membrane for the operation application. Acknowledge financial support of various funding agencies, KCSJ, Kerala State Council for Science, Technology and Environment, Department of Science and Technology, India, DRDO, for their financial support. And this is our group, the Professor Sabu Thomas. And this is my our Professor Sonny C. George. Thank you for your kind attention, and I thank all the organizer, Professor Marwa, for these wonderful opportunities, because yesterday I participated in 2 or 3 talks, and it is very excellent talk. Thank you.
Thank you, Dr. Joss. And we can have some questions. If you have any questions here, I can transfer it to you.
Okay.
Anyone have any questions? Any question here? Okay. Structure what?
The membrane.
Okay. One of our audience here is asking about the effect of the temperature and the effect on the temperature on the permeate or on the separation, and also the effect of temperature on the membrane structure.
But I can hear you properly. But
Repeat. Okay. The first question: the effect of temperature on the membrane structure.
Effect of temperature.
Mm-hmm.
Effect of temperature.
Yes. On the membrane structure.
On the membrane structure. Or on the evaporation. Which one? On membrane structure or evaporation? That is, I will answer this. Effect of temperature on evaporation, because if you are, this one is three-step process. That is sorption, diffusion, and permeation. Because if we increase the temperature, what happens? The molecule, the diffusion property of the membrane is increases, because it is the diffusion increases upon with the increase in the temperature. So its separation efficiency also increases with respect to temperature.
Okay, thank you. Anyone have any questions? Yeah. One of our big guests here asked about the shape of the membrane you apply. You apply for a flat sheet membrane or some type of spiral wound modules or hollow fiber. What's your type?
Reusability or shape? Which one?
Flat sheet, the shape of the structure of the cell for testing the membranes you use.
Yeah, that is a very, we are the same membrane. We got 100 micrometer, 1 to 100 micrometer, 100 to 150 micrometer thickness is there. As that same membrane we can use for the SEM.
Flat sheet, yeah? Flat sheet.
Yeah.
Flat sheet.
Pardon?
Flat sheet.
Ah, sheet, yeah.
Flat sheet, yeah. Yeah.
Yeah.
Thank you. Flat sheet. Is there any other questions? Okay. Thank you, Dr. Joss, and greetings to Professor Sabo. I'm hoping to see you soon in nature.
Oh, so sure. Thank you so much, Professor.
Bye.
Okay, after this pandemic situation, we'll meet together in Kerala or in Egypt, in any international conference. Sure. Then I welcome all the delegates to Kerala.
Yeah, we're sure we will go to Kerala. Thank you.
Yeah. Thank you so much.
Second speaker is Dr. Marwa. He is the associate professor in the Department of Civil Engineering in ITT Madras. His research interest includes the water and wastewater treatment using membrane angles, emerging pollutants removed by advanced oxidation processes, trace organics and nutrients removal from roots and materials from solid waste. Dr. Kumar, do you hear me?
Yeah, yes. Thanks, Professor Heba.
Yes.
Hi. Are you able to see me and hear me as well?
With you, I hear you.
Yeah, okay. So, first of all, before beginning the talk, I would like to thank the organizers, right, starting from Professor Ahmed and Professor Marwa, then Professor Heba. All three of you were there at IIT Madras, and I'm just going to present our collaboration work here and also the other things which we directly do here at IIT Madras, right? And once again, good morning to all of you, and good afternoon for somebody hearing in India. And for others, it may be like a good evening or probably like a good night or early morning. And with this, I share my screen and I will stop the video for the lecture. After that, I will really on the video, right? I stop here, then I will share the screen.
Okay.
Could you able to see the presentation?
Yes, you can start.
Yes?
Yes, you can start the document.
Okay. So the presentation for the day is the synthesis and application of TFN membranes, thin film nanocomposite membranes for water purification, wastewater treatment, and desalination. Because basically, I'm an environmental engineering by specialization. I work on water purification as well as wastewater treatment, and we also work on brackish water treatment and as well as desalination. So desalination is the very new addition to our laboratory. Otherwise, we started working on water purification as well as wastewater treatment. So today's talk, I'll be highlighting about 3 things, right? One is about the basic membranes, which is really used for water purification, and another by the membranes which we prepared it for nanofiltration purpose and reverse osmosis. So the membrane which we prepared is the mixed matrix membrane for water purification. So I'll also share the experience that we had, right? And I also like to take some questions towards the end. So before going into the actual technical details of it, so we need to understand the water demand, right? So the RO and other techniques are getting popular mainly because of the water demand, which we really realize. So I just put the table realizing the water demand in India in the context of year 2000, 2025, and 2050. You can see that this is the billion meter cube of water which is really required every year, right? So nearly it is really getting doubled. And the other thing, irrigation, also we need more amount of water, and the domestic is also really increasing population, also really producing the domestic wastewater. So the availability of water is really decreasing, but we need to provide the water supply to the public. People are working on generating water from different sources, including the seawater and recycling of the wastewater as well. So once you try to recycle the wastewater, and we have a variety of pollutants, right? So basically, earlier stage, we only remove the organic matter, nitrogen, phosphorus, along with metals. And these days, emerging pollutant is, or emerging contaminant is a term which we really come across when you really go for a water purification or wastewater treatment. So obviously, seawater, it started getting polluted by the emerging pollutants, but it is not really a big problem there. But when you see the emerging pollutants which are really present in water or wastewater, they include pharmaceutical compounds, surfactants, flame retardants, industrial additive, pesticides, and personal care products. All these things are really termed as emerging pollutants, and somehow they will really bypass the wastewater treatment plants. Ultimately, when you really discharge the wastewater, it will really end up in water resources, either it is a groundwater or maybe like a surface water. So normally what we do in wastewater treatment is, it is really a 3-stage process. First is a primary treatment, followed by secondary and tertiary treatment. Tertiary treatment is really introduced in the later stages, but in conventional treatment plants, if you see in developing countries at least, you have only the biological system where the sludge is really settled down. Then later we just go for the chlorination and we really send the wastewater for disposal or some other purpose. But obviously speaking, the secondary treatment is really not able to remove this emerging pollutants. That's why we really introduce the tertiary treatment system to really take care of the emerging pollutants along with other metals as well as NNP, which is really coming out from your secondary treatment. So what are the components of your secondary treatment of wastewater is, you merely have the filtration or any one of this in combination with this coagulation, flocculation, or sedimentation, filtration, followed by your normal carbon adsorption, or probably like an advanced oxidation. And finally, you have the membrane filtration and disinfection, and it will be really sent to the reuse goals. So what are the technologies which is really available? Right, so all these are really available, either an advanced oxidation process for removing the emerging pollutant, or a membrane technology starting from ultrafiltration, nanofiltration, RO, and combination of this with different schemes. Then you have the adsorption and other sorption exchanges, including ion exchange, or the combination of it. But if you look into closely a filter, which is really used in a household, because this is the filter which I really use in my household. If you see here, it is a 4-stage process, 1, 2, and 3, and 4. If you really arrange them, this is a sediment filter, then you have a carbon filter for adsorption and UV disinfection, and the membrane. So I have a very cheap price filter. That's why it has the NF filter here. So obviously, if you go for a high-end filter, highly priced filter, you will have the combination of NF plus reverse osmosis units. So what I'm trying to say is, if you really compare the water purification in terms of which is really penetrated into your foams to a bigger treatment system, as well as the wastewater, membrane technology is kind of not able to be separated from it. So obviously, membrane of different combinations are really used in your wastewater treatment plant and as well as water purification plant. But only constraint we have is we need to select the membrane technology based on the requirement of pollutant which we really wanted to remove. Either a bacteria or a virus, or maybe like an emerging pollutant, or maybe like any metal ion, or maybe like any dissolved solids which you wanted to really see it. So why I wanted to really stress on this particular point is, when you doesn't need an RO, please don't really go for an RO technique. But if you really wanted to treat the water with NF, you can really go with this, because all these membranes have different cutoff. The third day of the conference, obviously you understand what is the pore size of different kind of membranes, starting from membrane filtration, microfiltration, ultra, nano, and reverse osmosis. If you really see that, the energy required for RO is really 25 times really higher for compared to your microfiltration membrane in terms of kilowatt hour per meter cube of your wastewater related. But in the other side, if you compare your microfiltration membrane with respect to your RO membrane on a given pressure comparison, the flux is really 4 times higher you can get it in the microfiltration membrane in terms of liter per meter square per day, or LMH, which can really see here. And the typical advantage of membrane technology, why it is really getting so popular, is it can be really formulated to any shape and any size, right? You can really make nanofiltration membranes, right? You can customize based on the requirement of how much meter square area you really require for this. So that's why it is really have a unreplaceable position in terms of water treatment as well as wastewater treatment is really concerned. Now, so people are really going for the modification of membrane surface. There are different techniques which is really available: photo or reduction initiated surface grading, chemical reaction on membrane surface, or maybe like a physical coating and adsorption. But what we really do in our laboratory is we really focus on surface modification using nanoparticles. So the previous talk by Professor Thomas really reduce my job of explaining like how do we really coat it. So I really take out some point of some time from there, and I really highlight what we really mainly focus on. So we really do on incorporation of membrane surface, blending nanoparticles with membrane solution, and we really work all these nanoparticles for the preparation of our TFN membrane. So it is a titanium dioxide, zinc oxide, or silver, or graphene oxide, or combination of this. And we also use amino clay very recently to really get a high flux membrane. Okay, so this particular lecture, I'm going to give you 3 examples, as I said before. So we use the titanium nanotubes. That is the first study. We use it for NF membrane preparation. And later we used ZO for our RO membrane, zinc oxide for our RO membrane, the combination of zinc oxide plus graphene oxide for our RO membrane. And finally, I'm also going to highlight about the photocatalytic membrane, which we really prepared using PAO, right, of different things. So this is the methodology we followed. So titanium nanotubes we really prepared, and their size is really 200 nanometer to 20 micrometer in length. And for a graphene oxide, we use the modified Hammers method with the graphite powder as well as potassium permanganate, and we prepared a nano sheets, and their size is really given here. And in the zinc oxide, we prepared 3 different configurations, starting with spherical, flower, and rod shape. For spherical, we use the soldier method because we prepared using the zinc acetate and the oxalic acid, and we prepared the zinc oxalate gel, and the diameter of typical spherical particles are 15 to 20 nanometer. And for the flower and rod, we use the hydrothermal method for preparing it. But for making this difference between flower and rod, right? So we use the ratio of the molar ratio of NaOH to zinc acetate, and we control the ratio of OH hydroxyl ion to zinc at 4 for flower and 10 for preparing the rod-shaped nanoparticles. So these are all the TEM image of the nanoparticles and the nanocomposite, right? So the prepared TANTs, graphene oxide and zinc oxide of 3 different shapes, spherical, flower and rod. And we also prepared the composites. The preparation of the ZO and ZNO composites, right? So first zinc oxide nanoparticles were ammonia functionalized with 2 weight percentage aptas. Then later we prepared the graphene oxide zinc oxide nanocomposite using a simple ratio of 70:30 with weight to weight ratio for graphene oxide and zinc oxide. So thin film nanocomposite membranes, right? It's a flat sheet membrane. We have really prepared it, and the first it was really the polysulfone matrix, which is really prepared using the phase inversion technique with 20% polysulfone and 1 weight percentage in 79% of NMP solvent. And once the PF surface is really formed, then we move on to the interfacial polymerization, right, with 2 weight percentage MPD and 1 weight percentage of CSA and 0.82% of SNS. So we followed a particular recipe. And if you wanted to go with the preparation of TFN membranes, right? So TFN membranes is nothing but the nanoparticles are included in the PA layer, right? So the required quantity of ZO is mixed in the NPD solution, and the same methodology was really repeated. So we have the PFC membrane, which is not with nanocomposite or the nanomaterial. So TFN membrane, we have the nanoparticle in it, and we use different proportion. We try to see the property and the performance of the membrane. So this is the picture which showing you the philosophy behind it. So we just go for the phase inversion for preparation of the PSF, and after preparing this, during the preparation of your interfacial polymerization, we add the required quantity of your nanoparticles. This case, I just simply given it as TANTs if I wanted to prepare using the membrane with this, and ZNO, which is functionalized with amino ions, then we added with the ZO to prepare the ZO. Right? So this is represented as TFC. Then this composite is really added. Then you have the TFN membrane. So we have the thickness of these layers kept it as 0.2 to 0.4 micrometers. Right. So for preparation of the mixed matrix membranes, so what we do is we really blend the TiO2 nanoparticles in the PSF solution itself, and we really prepare the PSF support on a polyester node. So if you wanted to prepare the nanofiltration, you have the recipe, and if you wanted to prepare the RO, you also have the recipe here. So only difference is we just increase the PSF percentage, and we add also the PVP in it. And for coming to the testing of the membranes, we have the Sterlitech testing kit for the flat sheet as well as the hollow fiber membranes. But for this particular work, I'm going to really represent only the flat sheet membranes, and we have 4 parallel lines to really test it. It is a automized thing. You can see the parameters in the touch screen where you can really control all the settings here. This is the other close look of the skid which you have. So you prepare a membrane. From that, around like 42 centimeters square of the membrane area is really up here, and you can really conduct the studies. So if you prepare like ZO, ZNO, and the combination of GO, ZNO, then you can use all 4 skids, right? For different materials, you can dedicate each one of them, and parallelly you can really test the performance of the membrane module. So this is especially for the hollow fiber portion of this membrane module. So this particular experimental setup is under our laboratory, and we can freely use it for our all hollow fiber as well as the flat sheet membrane analysis. So coming to the result of TFN nanofiltration membrane with the addition of TANT nanotubes, right? So I'm highlighting only the major result here. We measured the contact angle. So with the increase in TANT content, the contact angle is really reducing. So it induces the hydrophilic nature of the membrane surface. And if you see the surface roughness, the pristine nanofiltration membrane has surface roughness of 60.9 nanometer. But if you increase the TANT content, then obviously at 0.05, it was the lowest. So which is giving a very smooth surface here. But when you increase more and more, obviously, the surface roughness is increasing because of agglomeration of the particles here. So it is our best judgment to really select which membrane we really want based on the flux which we can really attempt here. So for this particular nanofiltration membrane, we applied a pressure of 7 bar and we conducted at 25 degrees centigrade. But the skid also has the chiller, which can really vary the temperature, and you can find out the effect of temperature on the clean water flux through the particular membrane. So for the best case of 0.05% TNO2 loading, so we could able to get water flux of 50.1 liter per meter square. We would suggest that if you wanted to go for a TNT membrane, then obviously we can support with 0.05 weight percentage. So what is the application we really do here is we apply this particular membrane, really retain the pharmaceutically active compounds, nothing but the emerging contaminants which I introduced in the first slide. So we took 3 emerging pollutants, metronidazole, triclosan, and carbamazepine, each at 1 milligram per liter. When they are really present in the water and really pass through, and we change the different pH and try to see that how much is the removal percentage of metronidazole, triclosan, and carbamazepine. So almost from this particular data, the retention of the pharmaceutical in the enough filtration, mainly because of absorption, was really happening here, and both the membranes were really producing a good result, right? But if you really go for the long-term performance with this TNT-loaded NF membrane, the performance was really very good in terms of flux compared to your TFC membranes. So partially the removal of your emerging pollutant can really happen in the NF membrane. That's what we really find out from this particular approach. In the second thing, which we use the TFN RO membrane only with ZNO, the similar observation we take it for the contact angle as well as the surface roughness. The results are given for spherical particle ZNOS, and it's compared with the pristine, and we also given the result for flower shape, right? So particles. So we also had the result for a rod shape, which I didn't give it here, but you can see here the ZNO value of spherical is 0.01, the surface roughness is 15.96, but when you really increase it, it is really increasing the roughness of the membrane. The same thing, the contact angle with respect to increase in the ZNO concentration, the contact angle is really reducing. But again, I said like this is the compromise between which you want, the salt rejection or probably your water flux. Right. So this is the graph which is showing the ZNO content in the membrane to water flux and ZNO content with respect to salt rejection. You can see here ZNOS is really performing very well. The reason because it has the smaller size ZNO nanoparticle, right? And also it has a higher affinity for adsorption of your water, which makes the permeation of water, which is really more through this particular membrane. So if you see the size also, if you notice, the spherical particles has very smaller size compared to your flower and rod shape. And the similar thing, if you see the normalized flux, the ZNOS spherical particle of 0.02 has showing very good result in terms of normalized flux. So to make the fouling to really happen, we use the humic acid solution along with calcium fluoride and NaCl. We added it, then we just find out. But it is really performing good compared to your pristine membrane. And coming to ZO ZNO, because ZO and ZNO together will produce the higher hydrophilic functional groups, increased hydrophilicity, and higher affinity of ZNO nanoparticle to facilitate the water absorption. Not only that, efficient dispersion of ZNO nanoparticle is really seen here because of from the contact angle as well as the surface. And if you see here again, the spherical particle and the flower and the rod-shaped particle of CZNO is really given here. You can see that like ZNOS is 0.01 is 21.43, then it is really increasing slightly, then it is increases drastically at 0.0. The similar observation can also be made from F0 to But if you see the contact angle on the other side, the contact angle is really decreasing with respect to increase in ZO, composite content from 0.01 to 0.03%. And this is a comparison of the performance of ZO membrane, ZO only, ZNO only, and ZO ZNO. And we also added only with AG, and we have the combinations also. So if you see here, the combination is really doing very good in this range of 16 to 0.01 weight percentage, and the water flux also really very high, and the salt rejection is really very good. So this is the condition, and we see here that the ZNO spherical particle is really produced higher water flux, and the salt rejection also really very close to 97%, whereas at 0.01% it was really as good as 99.1%. And the reason being smaller size of ZNOS, which is effectively prevented the GO nanoseeds from stacking together. And this is our new approach. We mix the ZO as well as silver nanoparticles in it at a ratio of 70:15:15. Then the water flux was really very high compared to the other. Right? And this. And yeah, thank you. And these are all the other research which is really in progress, right? And the last study, which I really wanted to highlight very briefly, is photocatalytic nanofiltration membrane we prepared with TiO2, right? So we prepared the polysulfone membrane mixed with TiO2 up to the level of 1, 2.5, and 5 weight percentage, and the contact angle is found to decrease with respect to the increase in TiO2 percentage. And this is the cross-sectional and top view of the membrane to show that like there is a continuous pores through which the water is really passing. And for this particular thing, what we have done is we take the base sheet and we created a pattern in our lab, right, to really channel for water to flow. Then on the top, we provided the spacer. On top of it, we put the flat sheet membrane, which really prepared in our lab. And we have the reactor, and we framed this particular membrane module, and we really assembled for our membrane purpose, right? And what we do is, this one is really representing of the membrane frames, 3 numbers we really prepared here, and which has a total area of 0.28 meters square, and we used it for photocatalytic separation, because one biggest problem is separation of the catalyst. So what we did is, catalyst is already coated in the membrane surface, and we used it together for advanced oxidation as well as water treatment. So we applied it for metronidazole removal, MNZ, and we operated at different HRTs. The flow is really corresponding to 10 liters per hour, which correspond to 60 minutes HRT. And we could able to see that the MNZ removal was really good, but not really very high compared to the conventional thing. It requires that we need to increase the TiO2 content, which are really in progress. And the performance of the membrane is also really very good in terms of continuous cycles. The repeatability is really very good for the membranes. And coming to the summary, the membrane rejection depends on speciation of the compound membrane surface charge and feed solution pH in terms of emerging pollutant removal, and 0.08% of combination of ZO/ZNOS is really good, and TiO2 2.5 is good, able to oxidize the pollutant which used. So the major conclusion, membrane technology has huge scope in terms of water supply, water use, and closing the water loop and water cycle, and reducing the energy cost in membrane process would be the goal for future, and we work on nanoparticles to reduce the energy here. And thank you very much. And I would like to acknowledge Professor Pradeep, Department of Chemistry, IIT Madras, Professor Raghuram Chetty, Department of Chemical Engineering, IIT Madras, Professor Marwa, Heba, and Professor Ahmed from NRC Egypt. And they are all my counterparts from Egyptian side in a DST project, and all my research scholars in EWRE division, IIT Madras. So apart from that, we also really work on membrane bioreactors, which we have a setup, and we work on the hollow fiber membrane modules for treating the domestic wastewater contaminated with emerging pollutants. And we also have the smaller photocatalytic reactor for separation of the catalyst. This is the beginning which we started here, and we really upgraded to a mobile unit. And this is what we have right now. And thank you very much. And thanks for the opportunity.
Thank you, Dr. Kumar, for your interesting presentation. Any questions?
To ask about the testing conditions of nanofication of the restaurant. What is the person? What is the sample coverage? Are we only testing sheet in grade or have we tried to learn in grades?
Dr. Kumar, one of the audience here asked about the conditions for testing of nanofiltration and outcome membranes. About the recovery of the membranes and feed pressure. Do you hear me? Dr. Kumar?
Yeah.
One of the audience asked about the conditions of the testing membranes, feed pressure and the recovery.
Flow. The pressure was really the 20 bar, which you used for RO. NF, it was really 7 bar.
From 20 to 7, NF 7 bar and RO 20 bar.
Hello? Heba, I cannot really hear you very clearly because of the echo, probably.
Around feed, around recovery. Around the center recovery.
Sorry?
The percent recovery of the system membrane.
You're asking about the membrane type or?
Recovery percentage.
Recovery.
Yes, recovery.
See, this is actually like a continuous study, and we have the chiller tank, and it is really recycled back to the chiller.
Okay.
And we have the feed tank, and all the reject is really put in the feed tank, and we measure only the permeate.
Okay, thank you.
It's continuous and recycled.
Okay, thank you, Mr. Kumar. So, thank you.
Yeah, thank you very much. Thank you.
Next speaker is Professor Marwa Shalaby. She's professor in chemical engineering and bioplant engineering research division. She's a member of Flagship Membrane Group. She has agreed experience in membrane processes development, environment, and industrial scale optimization for spiral water review and desalination and water treatment with application of nanocomposites and its green sciences serving sustainability goals. She has 50 international publications, articles, and granted papers.
Good morning, everybody. Today, I present my talk on the recent trend in oil-water emulsion separation and its different techniques. We have selected to talk about this topic due to its, I want to say, it's a hard composition to be dealt with. as oil-water emulsion is one of the great problems found. In this presentation, we will talk about what's the problem. We will outline the problem. We will have some highlights for the classical treatment technologies. We will highlight how membrane processes can solve such problems and the challenges going through membrane treatment and how to reduce and what's the innovative approach for the tailoring for these membranes to cope with this separation process. And finally, we will go to the economics and how the membrane separation have an economic point of view to be used in this application. And finally, the status of the membrane technology now serving in the oil-water emulsion. We can begin to know that oil was found in its insoluble matter. And when we say insoluble, we can go through the three states of the oil. To go is a free-floating oil, which is the simplest one, the dispersed, and the dissolved, which go to the emulsified oil in water. As you can see here, you can see that this type is seems to be fully dissolved. So we are talking about less than 20 microns in the size of the oil droplets, which goes to another problem that the oil structure is not dealing with just such the pore size, because the oil can change its droplet shape to go through the pores, and so can make such problems when dealing with. Also, the problem which makes it high obligation for taking account this problem is how to get this oil for reuse and get benefit. Also, how to be environmentally safe in its disposal. The sources of oil, as all of us know, it's come from many sources at the paint industry, the cosmetics, the metal processing. But the main one and the huge amount comes from the petroleum refineries. The ecosystems and the ecological parts of the environment is highly harmed from this disposal, which can be caused in many regions in the world. Such areas in the world have regulation for discharge permissible limits. Some areas like Europe, France, Australia have stringent regulation for this. Others don't have. Okay. If we are talking about the oceans and the oil spills, all of us know for the onshore and the offshore production for the oil. Some of us don't imagine that oil also can make air pollution, because it has some evaporation for the hydrocarbons, which goes to the atmosphere and increases the percentage of air pollution. Okay. What's for the classical technologies which can be used for solving such problem? As you can see here in this slide, you can see that when we are talking about the emulsified range, we can think of electroflotation, electrocoagulation, adsorption, and so membrane filtration. Other than this, if we are talking about dispersed or free oil, it's very simple to use some separators like hydrocyclones or some advanced oxidation processes, Fenton oxidation. But when we are talking about or when we are going away from the classical technologies, we are talking about a method to recycle back the oil, to recycle back the water. How to get both of them, how to get benefit of them. When we are talking about adsorption, we can take both benefits, not by oil biodegradation, which is used with high efficiency, but it requires a long time and the loss of the oil value, because it goes through to go to degradation. But for adsorption, by using organic or inorganic porous media, the situation is completely different to get the oil back. When we are going to see the membrane technology to be a more innovative one when compared to adsorption or some types of separations, we can see here that sure, when we are talking about 10 microns or 10 or below, smaller than this, the 10 microns in size in the emulsified phase, we are talking about ultrafiltration, microfiltration membranes, and not to go to the nanofiltration. Both of them will be suitable. Here you can see an example which already used one of the greatest companies in America, in USA, United States of America, using PAN, polyacrylonitrile, for producing UF membranes. And here you can find, when controlling the molecular weight cutoff to increase to 100,000 Daltons, the percentage rejection reaches is lower to be 97, while the other was 99, and the permeate flux was highly enhanced. Here we want to say that the commercial applied membranes in the field of oil-water emulsions were found in around 3,000 installations. It was applied more than 20 years ago for many types of the membrane and many structures. Structure of the membrane used, like the modules for the flat sheets, as seen in the slide. Also, there exists some manufacturers for the spiral wound for using in it, but the more familiar to be used with the commercial ones is the hollow fibers and the tubular ceramic membranes, which is more familiar to be used with the oil-water emulsions. Also, this is some examples for using the electrocoagulation before the microfiltration membrane and the compact system to be used for the emulsions or separation of the oil-water emulsions. Here we come to the challenges. How to solve the challenges going to membranes and its application in this separation technique for the oil-water. How to get rid or to solve the obstacle found, which is the fouling. Here, this is a slide to get us remember that if you have the irreversible fouling, it will be stagnant, it will be a irreversible problem to be solved. So we don't go to this stage. Here, some illustrations to highlight that as we get fouling, we can increase the original flux, G0, it decreases to get J1, and after washing go to again to J2, which is get some higher flux, but it can't reach the original one. Here, some of what I have said in my first minutes of my talk, that the oil droplets can change its shape. So it's very, very difficult to predict its behavior. So to solve this, we need to change the structure of the membranes to go to some what's that super hydrophilic structure. Super hydrophilic structure, as you can see, is a way here. This slide is illustrating it well. Here, if you can see the photo for the oil droplet, if we put it super hydrophobic and super oleophobic, both of them will be prevented. If we put the super hydrophilic and super oleophilic, both of them can pass. But if you control what's the structure you want for letting the oil to pass through the pores or prevent the oil and let the water to pass. So if you want this, we have to tailor the structure of the membranes to go through super hydrophilicity and super oleophobicity for the oil to be prevented. And this is very, very promising for the light oils. But for the heavy oil fraction, it's recommended to go through another pre-treatment separation technique before going to membrane, because it will be very difficult if you have a heavy oil fraction to prevent it from going through the membranes. Here is some illustration also for what we have said. Also, we need here to highlight that the polymer forming the ultrafiltration membranes have many types. We here highlighting the PVDF as one of the famous polymer forming membranes. And here also the PVDF is a hydrophobic membrane, but the enhancing of this polymer, changing its characteristics, and have many advantages: the resistance for the chemical attack, for the oxidation, for the high temperature, for the abrasion resistance. And this is some of the modification which is made by blending some additives to the polymer to enhance its activity and enhance its fouling behavior, to increase the flux recovery ratio, to increase the water flux which is obtained after being fouled, which is highly enhanced. Like if we have an example like the amphiphilic tri-block copolymer, when used with PVP, increases and be used for the synthetic solution for synthetic oil emulsion, oil water emulsion with 100,000 ppm concentration. Another examples for the same. Also, if we are talking about another polymer like polyether sulfone or polysulfone, many studies have been done in this way, also for the enhancement by means of chemical grafting. To change and go to the super hydrophilic structure is not easy. To go through it, we need to have some grafting techniques with different polymeric additives, like sulfonated polyether ketone as an example, which enhance the water flux and enhance the fouling or flux recovery ratio. Another grafting can be made by the polyronic tri-block amphiphilic copolymer, polyronic F127, and other examples which increases the flux recovery ratio by more than 70%. We have many examples. Also, the natural origin for the polymers, which is depending on the polyacrylonitrile, as we have illustrated in our example, which is the commercial one. Also, the application of the cellulose acetate, the modified ketosane, and some other polymers can be used and used many times. Here you can find in the references that all of them are recent trends in 2020 and 2 or 3 years before. The effect of the blending with inorganic additives like carbon nanotubes or the calcium carbonate with the block copolymers, also like the polyronic amphiphilic copolymer with the pan, plays also an important role to increase the flux recovery ratio to 97%, which is a very promising results. Here also we can go to the other side of the modification. Other than blending, we can go to the surface modification, where here we can see the difference when we have illustrated examples using surface grafting. We have illustrated other examples using blending. The last one will be the surface coating. Although the surface coating to modify these membranes have been done for PVDF and polysulfone and PAN, polypropylene, and also the permeate flux and the percentage rejection was enhanced. The fouling also, the increased time of recyclability and using the membranes is enhanced a lot. Some were using the interfacial polymerization as a coating deposition, others using some deposition or co-deposition techniques, other authors uses vacuum assist assembly. Finally, if we have to have some economic or cost index or cost prices for to see how this process can be profitable. Here, there's a simple comparison between using the electrocoagulation and using the evaporation unit, and compared with using the ultrafiltration. Here you can see that the electrocoagulation by using all of them using 12,000 ppm for the COD, and the electrocoagulation gives around 60% reduction. For the evaporation, it gives 96% reduction. For the ultrafiltration, it gives around 76% reduction. And if we put the highest capital cost, of course, will be for the evaporation treatment unit, and will be also the longest payback time, which is almost 1 year. But if we go to the least consuming expenses, which is ultrafiltration membranes, to get the shortest payback time, 0.2 year, and when compared also for the electrocoagulation, the ultrafiltration is the least. If we put here for the percentage removal, we can see that the percentage removal for the electrocoagulation about 60%, and the ultrafiltration is 76%. This means that it's already a promising technology to be applied. Also here, by comparing the membrane-based technologies with the dissolved air flotation, we have found also the cost for the membranes from $1 to $3 per meter cube, while for the DAF treatment for about $3.65 per meter cube. Finally, this means that the membrane application for the water-oil emulsion separation techniques is a promising and have a future trends to be applied. But it depends mainly on the hydrophilicity and how to be enhanced. Also, here as a final conclusion, we need here to govern the pore radius. As the pore radius decrease and the increase in surface pore density, this will enhance the permeate flux and enhance the oil rejection to be reached. Also, the control for the solvent and non-solvent demixing rate during the fabrication of these membranes also will play an important role for enhancing the pore structure and its homogeneity. All these conclusions we have said while going through our presentation. Finally, I want to invite all of you to join us in the Egyptian-German Symposium December 2021 for the development of spiral wound modules membranes for water desalination. Thank you.
Thank you, Dr. Marwa.
Thank you, Dr. Marwa, for the interesting lecture. A question about the performance of this membrane in the long run, and what about its performance in different types of oil?
Different type of polymers. Yes. Of oil, yes. We are talking about oil-water emulsions. Then we are talking about certain force droplet size. We are talking the droplet size less than 20 microns. When we gone down 20, 10, 5, whatever. We are not controlling its source. We are controlling the oil droplets. Then, as a conclusion, when using the membranes, it's a promising technology. For the polymer used for the membranes, the most familiar polymer to be used by many industries is the polyester sulfone, because it's one of the cheapest polymers to be applied in this wastewater treatment. PVDF is good, PAN is good, have many promising results, but it's a very expensive polymers. So the trends to be used here is using the polyester sulfone.
Professor Walid has a question.
Okay.
Yes, please. Can I ask a question, please?
Yes, we are hearing you.
Yes. Thank you very much, Professor Marwa, for this very impressive. You can say it is a lot of work about your development of membranes in Egypt, different types and different facilities. My question is, can we think about one can make everything? I mean, one membrane can work with oil and inorganic and organic pollution with high efficiency, or this is a dream?
I think it's not easy to have one membrane, because as I have said in my presentation, we are tailoring the structure with a certain charge for getting rid of the oil, because the oil is somewhat noisy for completing the process, because it may cause a high fouled surface, with causing high backwash cycles and high cleaning cycles, which causes the process to be difficult. So if I needed to target more than pollutant, organic pollutant, inorganic ones, and so with the oil emulsions, I need to have stages. The first stage to get rid for the oil, and then go back with another type of the membrane to be used selectively for another pollutant. Because when you are selective, you can be able for a good operation, good performance, and be able for get out of the maintenance problems. Because as you put difficult conditions or difficult pollutants in the feed, you will bear a lot of problems during maintenance and operation.
Okay, thank you very much. Thank you.
You're welcome.
And thank you, Dr. Marwa, for the great work. Really, very well done.
Thank you.
It is not a question, it's a comment. It's that Aramco in Saudi Arabia has this problem in one of their sites.
Yeah.
And the oil field produced water. This site was produced a very big volume, more than 100,000 cubic meters per day, containing free oil and emulsified oil, together with a lot of other contaminants. They cannot dispose that to the sea. They should out of the norms of disposal. And on the other hand, they need an important function for pure water for injection in the oil carrying layer to enhance the product that extraction.
Yeah.
So we made them a pilot test using a hydrophilic nanoparticulation membrane.
Okay.
This could remove easily the contaminants and give a quality of water suitable for injection without blocking the porous structure of the oil carrying layer.
Perfect. Perfect. Thank you, Professor. Thank you. Using nanofiltration is very good, because when we are talking about this ultrafiltration, it's one which is between the range, because we are talking about tight ultrafiltration. Because ultrafiltration, as I have said, go to grafting process, go to surface modification, go to thin film composite, because it's not a wide ultrafiltration, but it's very narrow.
And it was also hydrophilic.
Yeah, super hydrophilic structure. Yeah. Thank you. Any other questions?
The type of product of this process oil separation?
It's a type of biofouling, because it's have a high COD, have high organic compounds, organic contents. So it's very, very difficult, because the oil droplets change its structure to go to the pores. So the play or the trick here, how to get the membrane repellent for this oil to not to go to the pore and block it. So how to remove the biofouling easily, first one by one. So the backwash here is very important to get rid easily from these dirt or oil stacks over the surface of the membrane.
What's the rate of backwash?
The rate of backwash used here is very high, because here the most familiar one which is used is the hollow fiber units, and so they're using some of the air diffusing and others with the water backwash.
Thank you, Dr. Marwa. The second speaker, Associate Professor Dr. Sabri, Associate Professor of Biochemistry in Chemical Engineering and Biochem Department in the Engineering Research Division of the National Research Center, and the member of Flat Sheet Membrane Group. She has a long experience in the field of desalination water and wastewater treatment by using different membrane technologies, including membranes, polymeric membranes like FO, RO, and MS membranes. She has more than 18 international publications and many patents granted and underwritten from the Egyptian Academy of Science and Technology. Welcome, Dr. Ali.
Assalamu alaikum wa rahmatullahi wa barakatuh. Fabrication of modification of modified cellulosic forward osmosis membrane for drying concentration.
I speak about one of the most important problems facing the simulation sector in the world. As we know, desalination technologies, particularly the reverse osmosis process, have increasingly been adopted to produce fresh water from alternative sources such as seawater and brackish water due to water scarcity. But this, the application of this technology usually limited by two factors. The first one is the lower costs of the produced concentrated waste brine, and the second is the adverse impact of this influence on the receiving environment. Based on the literature, the conventional disposal techniques for brine treatment for brine, including discharge through an ocean pipe, this usually applied in coastal region. While in inland desalination plant, there are several options for disposal, like deep well injection or evaporation using piling or unlined evaporation ponds, or by irrigation of plants tolerant to high salinity. However, these all disposal techniques are usually restricted to high capital costs and unsustainable, and require and have drastic impact on the environment in the long run. Usually, there are several advanced and traditional methods for the treatment of such effluent, including thermal process, chemical techniques, biological methods, membrane operation. However, among all these technologies, membrane technology appear to be the most cost-effective method for rearrangement of for treatment such effluent due to produce high water quality with high recovery and produce valuable resources, high valuable resources. Also, on the other hand, forward osmosis process has great attention, forward osmosis process attracted great attention of research community and at the industrial sector due to simple configuration and low energy consumption. As the presence from this table, the table illustrates comparison of emerging treatment technologies for brine treatment. As we see, forward osmosis have the lowest energy requirement compared to these other emerging technologies. So the features. What is the forward osmosis process? The most appropriate definition of forward osmosis process in the literature, it is a membrane process without the application of any hydrostatic pressure. This means the water flows from low concentrate solid to high concentration solution, depending on the effect, depending on the difference of osmotic pressure between the difference of osmotic pressure of the solution
found on the either sides of the membrane. One of these solutions we can known as the high concentrated solution, or known as draw solution, and the other solution known as the feed solution. It is a low concentrated solution. Based on the water flux or the direction of water flux through the membrane, the membrane can be divided into several types. Generally, the water flux of the membrane can be explained from these equations, where a membrane water permeability coefficient delta pi is the effective osmotic pressure, delta B is applied hydraulic pressure. For FO, for reverse osmosis, the hydraulic pressure, the applied hydraulic pressure in the high concentration solution usually higher than the osmotic pressure. This means that the driving force is hydrostatic pressure, and the water permeates through high concentration solution to the low concentration solution through the membrane, and the water flux increases with increasing the hydrostatic pressure. For forward osmosis process, the applied pressure is equal to 0. The driving force is osmotic pressure. The difference in concentration between the two solutions, low solution and high solution, and the water permeates from low concentrated solution to the high concentration solution. The third type is the pressure retarded osmosis. It is intermediate between the forward osmosis and reverse osmosis process. Is the applied pressure in the high concentration solution usually less than the osmotic pressure. So it is one type of the forward osmosis membrane. The driving force in this type is osmotic pressure, and increasing in the applied pressure, decreasing the water flux. So the applied pressure or the hydrostatic applied pressure renders retarded the water flux of the process. One of the most important factors affecting the forward osmosis process is a forward osmosis membrane. Forward osmosis membrane plays an important role in the efficiency of the forward osmosis process. This means that to enhancing the forward osmosis process and the efficiency of forward osmosis process, we require ideal forward osmosis membrane. Ideal forward osmosis membrane must be having the following features. The active layer should be dense and ultra-side to have a high rejection rate of solute. The support layer should be thin enough and high mechanical strength. The membrane should have a high hydrophilicity to increase the water flux and fouling, and CP and the concentration polarization, usually internal concentration polarization, elevation. The membrane should have a wide range and temperature tolerance and oxidation resistance range. Based on this feature, the main objective of this study is the fabrication of modified cellulosic forward osmosis membrane via phase inversion method for brine concentration. The membrane prepared by non-induced or non-solvent-induced phase inversion. This method usually used for preparing membrane with asymmetric structure, with porous sublayer structure and dense skin layer. The second image represents the bench scale of forward osmosis unit.
which consists of membrane cell. The membrane cell is the effective area of the membrane, about 56 meters square, and the cell has two channels to circulate water or liquids through the membrane through two dosing pump to circulate the solution from high concentrated solution, from low concentrated solution, from feed solution to high concentrated solution through the low solution. I want to say that this work is a part of patent under reviewing, and I will okay, but I will present. I will.
I'd like to know too much about this work.
No. No. It is very easy. I speak about later results of my work. It is patent under review. Okay, so only I will present the membrane characterization at the optimum conditions. Okay, this figure represents one of the most important parameters affecting on the membrane performance is the polymer plane ratio between the active layer or dense layer or dense active layer and the sublayer or porous sublayer of the membrane. This figure represents the FGIR analysis of the prepared membrane at different polymer plane ratio. As we see, the peak intensity of the hydroxide group increase peak intensity increase with increasing the polymer plane ratio. The hydroxide group is responsible on the membrane hydrophilicity. So by increasing polymer plane ratio, the hydroxide group increase, and this is in the peak intensity of hydroxide group increases, and this is confirmed by the physical characterization of the membrane as water uptake, contact angle, as polymer plane ratio increase, water uptake increase, and the contact angle decrease. This table represents physical parameters of prepared membrane at different polymer plane ratio. These parameters including water uptake percent, velocity, contact angle, tensile strength. Also, this figure represents the membrane morphology or the morphology of prepared membrane at the optimum conditions. The picture one represents the top layer of the membrane, which appears as a sponge, and this sponge and this structure here. And the second picture represents the cross section of the prepared membrane, which confirmed the asymmetric structure of the membrane. The membrane have asymmetric structure with porous sublayer and dense structure active layer, spongy dense and spongy structure active layer. The third picture represents the top membrane layer, which consists of the polyester non-woven fabric. So this figure represents the effect of the solution liquid-molar ratio on the water flux. As we see from this figure, the water flux decreases with increasing the solution molar ratio due to due to internal concentration polarization, which make boundary area of salts around the membrane and which hinder the water migration from across the membrane from the phase solution to the low solution. Also, this figure represents the effect of the solution temperature concentration on water flux at the optimum ratio, as represented from this figure. The flux decreases with increasing molar ratio of the concentration, which decreases the concentration of the solution. This is due to two factors. The first is the high concentration of ammonia, which affect on the membrane performance, and also due to internal concentration polarization, as we said before. This internal concentration polarization make a boundary area of salts around the membrane and hinder the water flow through the membrane and decline the flux. This figure represents the effect of time on forward osmosis performance at optimum mixture ratio of the solution. The effect of time on forward osmosis membrane performance at optimal mixture ratio of the solution. As we see, there is no decline on water flux through the membrane at all the times. And this confirmed by the membrane morphology of the membrane morphology after application on dry concentration. The cross section represents there is no accumulation in the of the salts in the layers of the membrane. Also, the second picture represents there is no accumulation of the salts in the fabric layer. So the membrane before the application and after the application have the same performance. Polymer blending is considered as a time and cost-effective way to develop new material with desirable properties, which are not found in the individual polymers. The fabricated modification cellulosic forward osmosis membrane via phase inversion technique were used as membrane prime concentrator. The membrane hydrophilicity was increased by increasing the polymer blend ratio. The membrane physical distance, water uptake, contact angle, tensile strength were enhanced by increasing the polymer blend ratio up to 6. The modified cellulosic forward osmosis membrane accepted the highest flux equal 24.6 liter per meter square hour at the solution molar ratio 1:1 ammonium hydroxide ammonium bicarbonate compared with other molar ratio. Thank you.
Thank you, Dr. Anya. Any questions?
How we regeneration or rise after saturation?
Brian?
How we make a regeneration.
Regeneration after saturation by the membrane?
No, the rise.
The brine, there is several methods to regenerate the brine by zero liquid discharge. Evaluation process making crystallization to the high concentrated brine. The forward osmosis process decreasing the volume of this brine. Then we consume low energy to recrystallization or crystallization of such brine.
Okay, any other questions? Thank you, Dr. Anya. Next. Yes, Vita, Karen, Zerana, Master, Karen, Meditate, University, Chemistry Department.
My presentation
presentation outlines are general introduction, aim of work, materials and methods, membrane performance, systems, result and discussion, final conclusion. First, we start with the general introduction. As we know, Egypt has been suffering from severe water scarcity in recent years, and Egypt has been on the rail in other countries to support its rapidly growing population and development. The Nile River is the lifeline of the country and it serves the country's industrial and agricultural demand and the primary source for drinking water for the population. Water shortages are become a worrying problem as demand for fresh water exceeds supply, rapid degradation of energy. So we are searching for other sources to get fresh water from other sources as seawater and brackish water by desalination. What is desalination? Desalination is the remove or separate salts from saline water to give fresh water. Desalination are classified to two main types: thermal desalination and membrane desalination. Thermal desalination, which involves heating of saline water to its boiling point to produce water vapor, and then the vapor condensed to give fresh water as a multi-stage plant. Multi-effective distillation, low temperature evaporation. Second type is membrane desalination, using a semi-permeable membrane to separate the salt from the water to get fresh water as forward osmosis and reverse osmosis. In our work, forward osmosis membrane, what is forward osmosis? Forward osmosis is osmotic process in which a semi-permeable membrane is used, and the driving force here is the osmotic pressure difference, which helps the water to flow from the high concentration to low concentration. There are many advantages for overseas: low pressure operation, high water flux and recovery rate, less fouling frequency, easy cleaning. In this slide, the difference between forward osmosis and reverse osmosis. Forward osmosis, water diffuses naturally through the membrane from low concentration site to high concentration site. But in reverse osmosis, pressure is applied to concentrated solution, overcome osmotic pressure and force the water to flow from the high concentration site to low concentration site. There are two major types of forward osmosis membrane. There are many factors affecting the forward osmosis: draw solution properties, feed solution properties, and the operating condition and internal concentration polarization. Forward osmosis membrane, the two types: thin film composite, cellulose triacetate. First type, cellulose triacetate, thickness must be less than 50 micrometer. Don't have thick support layer, reinforced with polyester mesh as a mechanical support. High chlorine resistance, high hydrophobicity, limit flux, limited stability to pH, temperature, and microorganisms. Second type, thin film composite membrane, fabricated by supporting of ultra-thin selective layer on porous support layer, combine advantage of two separated layers and can lead to good FO performance. Top skin layer thickness ranged from 100 to 300 fabricated. In most cases, for VA, for polyamide support substrate usually consists of polysulfone or polyether sulfone cast over a polyester fabric. The key factor of optimal thin film composite forward osmosis membrane, including complying of extremely thin selective layer with high water permeability and solid selectivity. Support layers must be thin, highly porous, and minimally twist to diminish the ICB. Aim of work, development and optimization of polyether sulfone mixed matrix non-composite forward smooth membrane for desalination. Materials used in work: polymer, solvent, additives, organic and inorganic additives, membrane preparation, use phase inversion method. After prepared membrane, we have made some characterization. We make scanning electron microscope to identify the membrane morphology, and XRD FTIR to identify chemical composition. Finally, physical properties, water uptake, porosity, and contact angle. This is the FO performance system experimental setup as we saw. Water flow from feed solution to draw solution through the cell. We will discuss discussion and the result as shown in the figure XRD for graphene oxide, titanium dioxide, and non-composite of graphene and titanium dioxide. Graphene oxide show characteristic one peak at 2 theta 10, and titanium dioxide show two phases, alpha phases, and rotile, and the composite is the red color in the figure, have a low intensity due to incorporation of the non-composite. Here is the FTIR for the non-composite membrane. This FTIR confirms the XRD. We have made many characteristics as can electromicroscope to the top and the bottom surface and cross-sectional surface for the prepared membrane at optimum condition. Physical parameters, as we saw in the table, while concentration of non-composite graphene oxide increase, water uptake increase, and porosity increase, and contact angle decrease, indicating increasing of hydrophilicity till the optimum in G5. In this table, effect of titanium increasing is the same. Increasing the titanium dioxide concentration, water uptake, and porosity increase, and contact angle decrease, where hydrophilicity increase. In membrane performance, we take the optimum concentration of graphene oxide and change the concentration of titanium dioxide. Water flux increase and the reverse salt flux decrease to the minimum, and the salt rejection rate increase to the maximum. This figure shows that the forward smooth increase to the maximum, and the reverse salt flux decrease to the minimum, and the salt rejection rate increase to the maximum. This is comparison between finally we achieved the minimum salt. We achieved the minimum reverse salt flux and a high forward smooth water flux and the highly salt rejection flux. Conclusion: the properties of polyether sulfone mixed matrix forward smooth membrane were successfully modified by incorporating a different amount of nanoparticles ranging from 0 to 1% weight into the substrate matrix using phase inversion. Results show that the hydrophilicity and porosity of polyether sulfone with the graphene oxide nanocomposite was improved upon addition of titanium dioxide. The higher the titanium loading, the lower the contact angle value, more hydrophilicity, and the greater porosity value. It is clear that the graphene oxide and titanium dioxide nanoparticles are uniformly dispersed in polyether sulfone matrix surface of blended membrane becomes thicker than that of unblended membrane, formation of material containing both hydrophilic graphene oxide and titanium dioxide can be lead to change in chemical functionality and separation performance of membrane. Thank you.
Thank you very much, class. You already did a good complete and complete. Thank you. Any questions? Yes, thank you. We will go to the coffee break. And the next session will begin at 1 o'clock.